Welcome to AI Paper Podcasts. Today we're exploring a really fascinating paper, Analyzing Modern NVIDIA GPU Cores by Rodrigo Huerta and colleagues.
Yeah, this one's important if you're involved in AI or HPC. GPUs are, everything right now, especially for these huge models.
Exactly, but getting solid info on how the latest NVIDIA GPUs actually work under the hood, surprisingly tough.
Right, it's kind of a black box. This paper really tries to pry it open.
They reverse-engineered key parts of the Ampere architecture, think RTX A6000, looking at how the hardware and compiler interact. Things like instruction issue, the register file, memory access.
And the result is a simulator model that's way more accurate than what we had before. We're talking a big drop in prediction errors compared to tools like Accel-sim.
Yeah, a huge leap. And it even seems portable to other architectures like Turing. So today we'll get into why they did this, how they did it, the key discoveries about, control bits, scheduling, caches, and what this new model means.
Sounds good. It's about time we got a clearer view of these modern cores.
So maybe let's start with the motivation. Why is this kind of reverse engineering even necessary?
Well, the core problem, as the paper points out, is that a lot of academic research on GP1 microarchitecture is still based on really old designs, like NVIDIA's Tesla architecture.
Which came out when? 2006?
Exactly.
Yeah.
Ancient history in GPU terms. Modern GPUs, especially with AI workloads, have evolved massively since then.
So basing new research on those outdated models could lead to wrong conclusions.
Pretty much. Findings might just be inaccurate or miss the real bottlenecks in today's hardware. The paper's goal was basically to fix that.
To give researchers a more accurate blueprint of a modern GPU.
Right. To understand the actual design choices in something like Ampere, so future work can identify, real opportunities for improvement rather than optimizing for a phantom architecture.
It makes sense. You need an accurate map of where you are before you decide where to go next.
Precisely. And they looked at quite a few key areas.
Like the issue stage, how instructions get sent off.
Yeah, the issue stage, the fetch stage before that, the register file, including its cache, the memory pipeline details, latencies.
And they built a whole new simulator model based on it all.
And validated it extensively. Plus, they dug into things like the instruction prefetcher and the impact of those register file caches.
Okay, so the big question, how do you actually reverse engineer a modern GPU core? It's not like NVIDIA publishes detailed schematics.
No, they definitely don't. The main technique is micro-benchmarking.
Meaning?
You write very small, very specific pieces of code designed to stress just one particular part of the hardware. Then you measure exactly how long that tiny piece of code takes to run.
Like little experiments targeting, say, register access or memory latency.
Exactly. You wrap your target code snippet with instructions to read the GPU's internal clock counter before and after.
Ah, so you get precise timing.
Very precise. You run it, collect the timestamps, and analyze them later. It lets you infer things about the hardware's behavior, like how many cycles an operation takes, or if there are conflicts.
And they were writing these tests in CED.
Mostly even lower level. They often used handwritten SAS.
NVIDIA's assembly language, wow.
Yeah, you need that level of control to really isolate specific hardware mechanisms and, crucially, to manipulate the control bits within the instructions themselves.
Okay, you mentioned control bits before. They seem really important in these modern GPUs. What's the deal with them?
They're fundamental. It's a major shift from older designs. Instead of relying heavily on hardware at runtime to check for data dependencies, like using scoreboards, modern NVIDIA GPUs put a lot of that responsibility onto the compiler.
How does that work?
The compiler embeds these control bits into each instruction, giving the hardware hints about dependencies and timing.
So the compiler is saying, okay, hardware, the results of this instruction won't be needed for, say, 5 cycles.
Kind of, yeah. One key mechanism is the stall counter. Each warp, that group of 32 threads, has one. The compiler calculates the latency of a producer instruction and figures out how many instructions later the result is consumed. It sets the stall counter based on that.
And the hardware just counts it down.
Yep, decrements it every cycle. The warp can't issue another instruction from that point in the instruction stream until the counter hits 0.
What if the compiler gets it wrong? Sets the counter too low?
That's the catch. If the compiler messes up, you can get incorrect program results. The hardware basically trusts the compiler's stall count for these fixed latency instructions. It doesn't double check for read after write hazards in the same way a traditional scoreboard might.
Huh. Seems risky, but I guess there's an upside.
Definitely. The benefit is simpler hardware. Less area, less power spent on complex dependency checking logic. You remove a lot of wiring. It's a hardware compiler co-design trade-off.
Okay. There's also a yield bit.
Right. The yield bit is another signal from the compiler. If it's set on an instruction, it tells the hardware, don't issue another instruction from this same warp in the very next cycle.
When would you use that?
Usually when the oldest instruction of a warp isn't ready to go, maybe waiting for something else. It helps manage the pipeline flow at a very fine grain.
How do stall and yield interact?
Well, if the stall counter is already greater than 1, meaning the warp is going to wait at least 2 cycles anyway, setting the yield bit for the next cycle doesn't really matter. The yield bit is more for those situations where the stall count is low or 0.
Makes sense. Now that covers fixed latency stuff. What about things like memory access, where the compiler can't know the exact latency?
Good question. For that, they use a different mechanism, dependence counters. There are 6 of them per warp, labeled SB0 to SB5.
Okay, 6 counters. How do they work?
They start at 0. When a variable latency instruction, the producer, issues, it increments one of these counters. When its result is finally ready and written back, it decrements the counter.
And the consumer instruction.
The consumer instruction is told which counter to watch. It simply stalls, it won't issue until that specific counter goes back to 0. This handles read after write, raw, and write after write, WIW hazards, for variable latency operations.
What about right after read war hazards? Is that handled too?
Yep, similar idea. The producer still increments a counter when it issues. But the key difference for war is that the counter gets decremented only after the consuming instruction has finished reading its source operands. The consumer still waits for the counter to hit 0 before issuing.
So the instruction itself needs to encode which counters to increment and which to check.
Exactly. There are fields in the SAS instruction format. A couple of 3-bit fields specify up to 2 counters to increment, and then there's a 6-bit mask telling the instruction which of the 6 counters it needs to wait on all corresponding bits in the mask must be 0 for it to be ready.
6 counters doesn't sound like a lot if you have many independent memory operations happening.
It can be a constraint. The compiler might need to get clever, maybe have multiple producers target the same counter if they feed the same consumer, or sometimes reorder instructions to stay within the limit.
Is a counter increment immediate?
Almost. It happens 1 cycle after the producer issues. So if consumer instruction immediately follows a producer, the producer also needs to set the stall counter to 2. Just make sure the consumer waits long enough for the dependence counter increment to register.
Tricky timing. They also mentioned a dbar LE instruction.
Right, dbar.le. It's like a more flexible barrier based on these counters. It lets a warp wait until a specific counter is less than or equal to some value, and actually wait for other specific counters to be 0 as well.
When would that be useful?
It's good for things like ordered memory writes, where you know operations complete sequentially. You can use it to wait for just the first few to finish. Or it can help in reusing counters for managing both raw and war dependencies sometimes.
Okay, one last control bit thing. The register file cache hint.
Ah, yes, the reuse bit. It's associated with source operands. The compiler sets it as a hint. Hey, hardware, this register value might be needed again soon. If set, the hardware might cache the value in the register file cache.
To potentially speed up the next access and save power.
Exactly. Avoids reading from the main register file banks if it's already cached nearby.
All right, that's a lot on control bits. Let's zoom out to the GPU core itself, the SM. What are the main building blocks?
Okay, so at a high level, you've got the front end, fetch and decode units pulling instructions in, then the issue unit deciding what runs next, a control unit managing things, and allocate stage for resources, then the execution units themselves, some for fixed latency math, others for variable latency things like memory or special functions, and of course the register file, which we now know has regular, uniform, and predicate types, plus caches, L0 and L1, and the memory interface.
Let's focus on that issue scheduler. How does it pick the next instruction to run? It seems critical.
Super critical. For a warp to be even considered, its oldest instruction needs to be valid, not waiting on any data dependencies, which is where those control bits come in, and resources like the execution unit's input latch need to be available.
How busy are those execution unit latches?
Depends. If the unit handles half a warp at a time, the latch is busy for 2 cycles. If it's a full warp unit, just 1 cycle.
And constant cache lookups.
They happen right in the issue stage. Checks if the constant data is ready. Avoid stalls later.
What about reading from the register file? Is that checked at issue?
Not quite for fixed latency instructions. Register file read port availability is checked later in the allocate stage. If ports aren't free, then the instruction stalls there.
But variable latency instructions skip allocate.
Right. They go into a queue after the control stage and read registers when there's no conflict. And interestingly, fixed latency instructions seem to get priority for the register file ports.
Okay, so multiple warps could be ready. What's the policy? First come, first served.
Not exactly. Their experiments point to something they call CGGTY, compiler guided greedy, then youngest.
CGGTY. Break that down.
Okay, greedy means if the current warp being considered has its oldest instruction ready, the scheduler tends to issue it. It's greedy within that warp.
Yeah.
Then youngest means when the scheduler does decide to switch to a different warp, it picks the youngest one that has an eligible instruction ready.
Youngest, not oldest. Huh.
Yeah, counterintuitive maybe, but that's what their micro benchmarks showed, especially in the scenarios they set up with different stall and yield bit combinations.
And they confirmed that this policy works.
They showed strong evidence for it, yeah. Though they did note their experiments mainly confirmed it for warps within the same CTA, the same thread block. It might differ for warps across different CTAs.
Okay, moving up the pipeline to the front end. How do instructions even get fetched?
Each SM actually has 4 subcores. Warps get assigned round robin, like warp ID modulo 4. Each subcore has its own little private L0 instruction cache. Then all 4 subcores share a larger L1 instruction cache. There must be some arbiter managing access to that shared L1.
Do they prefetch instructions? Try to guess what's needed next.
Yeah, it's like it. The evidence points towards a fairly simple stream buffer in the L0I cache.
A stream buffer? How does that work?
When there's a cache miss, it basically just fetches the next few consecutive blocks of instructions from memory, assuming the program will likely execute sequentially for a bit. They estimated its size at around 16 entries based on their accuracy tuning.
And that simple approach works well enough.
Surprisingly well, yeah. They think it's because GPU code often has threads in a warp executing similar paths, and control flow isn't usually that crazy complex. So just fetching ahead linearly often gets the right instructions.
So much so that it performs almost like a perfect cache sometimes.
In many cases, yes. Which also suggests complex branch prediction might not give much extra bang for the buck here.
And the fetch policy is likely similar to the issue policy, CGGTY-like.
That's the assumption. Makes sense to keep fetch and issue somewhat synchronized so you don't have one waiting too long for the other.
Let's circle back to the register file. You mentioned regular, uniform, and predicate types.
Right, regular is the big one. 65,536 32-bit registers per SM, split across the subcores and their banks. Uniform holds values common across a warp, 64 per warp. Predicate is for conditional execution, 8 per warp, storing 1 bit per thread.
What about writing results back? Any bottlenecks there?
Each bank has a wide N24-bit write port. They did see load instructions getting delayed a cycle if they finished at the same time as a fixed latency instruction targeting the same bank. But 2 fixed latency instructions writing to the same bank didn't cause delays, which suggests there's a result queue, maybe for buffering and bypassing results directly to consumers.
And reading operands. Conflicts there.
Definitely. Read bandwidth is also 124 bits per bank per cycle. If an instruction needs 2 operands from the same bank, like an FMUL or FFMA, it can cause bubbles 1 or 2 cycles respectively. The exact read policy seemed complex, though.
And this register file cache, the RFC, how does that fit in?
It's a small compiler-managed cache just for operands from the regular register file. Helps reduce read port contention and save energy.
How big is it?
Seems like 1 entry per bank per subcore. Each entry holds 3 224-bit operand values, so 6 operand slots total per subcore. Tensor core instructions using consecutive registers cache them in their respective bank entries.
And the compiler uses the reuse bit to decide what goes in.
Yep. If the reuse bit is set for an operand, it gets cached when read. Later instructions in the same warp needing the same register at the same operand position might hit the cache. But they found an interesting quirk. Any read request to a bank operand slot seems to invalidate whatever was cached there, even if the current instruction could have used it. A simple invalidation rule, it seems.
Okay, let's shift to the memory pipeline. How do loads and stores work?
It's staged. Some parts are local to each subcore queuing, address calculation. Other parts are shared to data cache access, shared memory itself.
How many memory operations can each subcore handle?
They think each subcore can buffer about 5 memory instructions. And the shared structures, like the path to shared memory, seem to handle 1 request every 2 cycles from any subcore. So contention is possible there.
What about calculating the addresses? Is that fast?
Address calculation seems to take about 4 cycles per instruction per subcore. If all subcores are hitting memory hard, that could become the bottleneck, not just the shared path. They also estimated the queue before address calculation holds about 4 entries.
Did they measure latencies, global versus shared memory?
Yes, lots of latency measurements in the paper for raw war on global, shared, constant memory with different register types, data sizes. One interesting bit, global memory access was faster if you used a uniform register for the address. Probably simplifies address calculations since it's the same for all threads. Shared memory was, unsurprisingly, faster than global.
Any surprises with constant memory?
Yeah, a couple. War latency was higher than raw for constants. And it seems fixed latency instructions use a different, faster constant cache, L0FL, than explicit load constant instructions, LDC, which use a variable latency one, L0VL. They also measured data transfer bandwidth back to the register file at a 512-bit cycle.
Okay, so after figuring all this out, they built a new simulator model in Accel-sim. What did they change?
They pretty much rebuilt the core model, added support for all those control bits, stall, yield, dependence counters, modeled the L0 iCache with that stream buffer prefetcher, implemented the CGGTY issue policy, added the allocate stage checks for register conflicts, built more accurate memory units reflecting the measured latencies and queue sizes, modeled tensor core latencies based on operands, fixed multi-register instruction timing, corrected address handling issues. It was a major overhaul.
And validation, how did they check if it was actually better?
They ran 143 benchmarks from 12 suites on their simulator and compared the predicted cycle counts against actual hardware counters from 4 different Ampere GPUs. They also compared against the original Accel-sim. Metrics were mainly MAPE, mean absolute percentage error, and correlation.
And the results, was the new model more accurate?
Oh yeah, significantly. For the RTX A6000, the mean MAPE dropped by over 18% compared to vanilla Accel-sim. The average error against hardware was down around 14%.
That's a big improvement.
Huge. Accel-sim had errors over 100% on 10 apps. One even hit 543%. Their new model's worst error was only 62%. The 90th percentile error also dropped dramatically. Much more reliable.
They also looked at sensitivity, right? Like how much does that instruction prefetcher matter?
They did. Tuning the stream buffer size, they found 16 entries gave the best accuracy and confirmed that this simple stream buffer performs surprisingly close to a perfect iCache for most GPU stuff, likely due to the code similarity across threads. Branch prediction probably wouldn't help much.
So maybe just assuming a perfect iCache is okay for some simulations.
For speeding things up, maybe, if you're not studying the iCache itself. But they warned it can cause inaccuracies on benchmarks with tricky control flow.
What about the register file? Did having the cache or more read ports make a big difference?
On average, across all benchmarks, the differences were kind of minor between having the RFC or not, or 1 versus 2 read ports. But
there's always a but.
For specific compute-heavy benchmarks, it mattered more. Max flops got way faster, 44%, with 2 read ports, though accuracy dipped a bit. Cutlass Gem really suffered without the RFC, and only 1 port performance dropped 22%, showing how much it relied on that cache. Adding a second port helped claw back some performance.
So the best configuration depends on the workload.
Pretty much. Single port plus the cache seems like a decent baseline, but specific apps might benefit significantly from more ports or be hurt badly without the cache.
And the comparison between control bits and traditional scoreboards for dependencies.
Key finding. The control bit mechanism is way smaller in terms of hardware area, like 0.09% overhead versus over 5% for a comparable scoreboard.
Wow. And performance.
Performance was actually slightly better or comparable with control bits. Accuracy was similar too, so it's much more area efficient, especially as you pack more warps onto an SM like newer GPUs.
But scoreboards aren't totally useless.
No, there's still a valid option if the compiler can't, or doesn't, provide those control bit hints, maybe for some precompiled libraries or certain types of kernels.
And quickly, they think these findings apply beyond Ampere, like to Turing.
They validated it on Turing and found good correlation. They argue the core pipeline principles are likely similar across recent generations, even with additions like tensor cores or RT cores. Latencies might need tweaking, but the core logic probably holds.
Okay, let's wrap this up. What are the headline findings here?
We now have a much clearer, publicly documented picture of modern NVIDIA GPU microarchitecture, the CGGTY scheduler, the register file details including the cache, the memory pipeline bottlenecks and latencies, the simple but effective instruction prefetcher, and especially that intricate dance of control bits managed by the compiler.
And the big practical outcome is that much more accurate simulator.
Absolutely. An 18% reduction in MAP is a game changer for researchers needing reliable simulation.
Any key insights that jump out?
I think the effectiveness of simple prefetching is one. Another is how efficient the software-hardware control bit system is compared to scoreboarding. Really highlights NVIDIA's co-design philosophy. And also, how sensitive some applications are to register file details, like the cache.
Yeah, that hardware compiler co-design really seems to be the central theme. The compiler isn't just translating code, it's actively guiding the hardware's execution.
It's deeply integrated.
Which leads to a final thought. If the hardware relies so heavily on compiler hints via these control bits, what does that mean for security? Could crafted compiler output or manipulated binaries cause problems? And looking forward, how might this tight hardware-software link evolve? Will we see even more compiler control, or maybe different approaches?
That's a great question to ponder. The implications of this deep coupling are definitely worth exploring further.
Well, this has been incredibly insightful. Thank you for walking us through the complexities of this paper. For everyone listening, especially AI researchers and engineers, hopefully this gives you a better feel for the amazing hardware you're working with.
My pleasure. And definitely check out the original paper if you want even more detail. The authors also released their simulator code changes, which is a fantastic contribution.
We'd love to hear your takeaways too. How might these details impact future accelerator design? What are the next GPU bottlenecks we should be tackling? Let us know your thoughts.
And please join us again for future AI paper podcasts as we continue digging into the latest research. Send us your paper suggestions too.
Until next time, keep exploring.